Hey students, welcome back. This is 6.3. We're going to talk about Charles' law. What you will want is you will definitely want a calculator near because we have to do some calculations. You also need to remember our Kelvin formula because all of our temperatures have to be in Kelvin. So we're going to start by putting that right there. This is how we convert from Celsius to Kelvin. All right. So let's go ahead and get started. This is Charles' law. Ooh, we'll highlight in purple today. 6.3, Charles' law. This is page 37. All right, so what Charles' law says is it says a volume of a fixed mass of gas. So that means we have the same number of moles or our moles don't change at a constant pressure. So pressure is going to stay constant and not change here. So our volume and our temperature vary directly. If you remember, we said Boyle's law, they vary inversely. So when we're talking about this, we say that volume and temperature vary. Ooh, don't want to do that in a highlighter. All right. As the volume goes up, the temperature goes up, or vice versa. We could think of it as the temperature going down, the volume going down. And we could think of that in terms of like a basketball. If we leave a basketball outside in the winter, it seems to deflate, right? Or get smaller because the air is more compressed is really what it happens. So when we did it before with Boyle's law, we said P1 V1 equals P2 V2. But if we do the same thing with volume and temperature, since it's directly, officially we should have, let me blow this up just a little bit, V1 over T1 equals V2 over T2. Which this is totally correct, but I found it's a lot easier to kind of cross multiply and go ahead and get the fraction out, if you will. So we have V1 T2 is equal to V2 T1. And then this way I don't have to deal with numbers in the denominator because sometimes I'm not super good at that. So either or of these, but we definitely want to have these in our memory bank because that's what we're going to use. All right. And the big key here is all our temperatures have to be in Kelvin. We have to change all our temperatures to Kelvin first and foremost before we do anything else. Okay. So let's look at some examples here. And remember our formula for finding Kelvin we put right up there. So let's look at this first one. We have a sample of neon gas occupies a volume. Oop, there we go. Volume V1 at 25 degrees C, that's T1. What volume, that's what we're looking for is our question mark, V2, will occupy at 50 degrees C. This is T2. So just like I did with the Boyle's law notes, I'm going to write out to the side what I know. I know V1 is equal to 752 milliliters. And I'm going to go ahead and put T2 right here because that way I put it in the right order. So T2 is my 50 degrees Celsius. But remember, we need to change that to Kelvin. So I'm going to automatically add 273 right there to it. This is where our calculator comes in. Or maybe you just know this one, 323.15. That works too. There's our Kelvin. V2 is our question mark. And T1, we have 25 degrees C. So again, that needs to go to Kelvin. So we add 273.15, which gives us 298.15. All right. And now we're ready to just plug it in and solve, much like we did with Boyle's law. Since we rearranged it, we have V1 T2 equals V2 T1. All right, so let's just plug in what we know. 752 times 323.15 is equal to V2. That's what we're looking for this time, 298.15. Awesome. Now we need to isolate V2, so we do that by dividing by each side by 298. That way we can get V2 by itself. So we're going to divide each side by 298.15. Cancels over here, right? And that leaves us with V2 is equal to 752 times 323.15. That's not a 3. All right, 323.15 and divided by 298.15. All right, so 752 times 323.15 and divided by 298.15, and we should get 815. Now, let's make sure that that makes sense, milliliters. Let's make sure that makes sense. So our temperature went up, right? So our volume should have went up. So it went from 752 to 815. Yeah, that seems legit. Okay, awesome. Let's try another example here. All right. So we have our helium balloon filled at a volume. Oh, there's a volume. There's T1. The volume decreases, so that's V2. And we're looking for the temp in Kelvin. So we're looking for T2, but then it also wants us to take it to Celsius. So we've got a little bit of work here to do. So let's go ahead and write down what we know. V1 is 2.75 liters. Make sure my dot shows up. T2, remember I'm going to go ahead and put that there so I don't get them confused when I do the math. Ooh, that's what I'm looking for. That's my question mark. V2 is 2.46 liters. So my volume is going down, so my temperature should go down. T1, 20 degrees C, so we need to take that to Kelvin every single time. So this will be 293.15. All right, and that's our Kelvin. So plugging it in, we've got V1 T2 equals V2 T1. All right, we know we have 2.75. We're looking for T2. And we've got 2.46 times 293.15. So when we solve this for volume, we're going to divide by 2.75 on each side to get our temperature. I said volume. We're dividing to find temperature, but you guys are with me. T2 is equal to 2.46 times 293.15 divided by 2.75. Okay, T2, let's go ahead and plug that in. This temperature is going to be in Kelvin. So that'll answer the first part of our question. Divide by 2.75. So our answer here, we should get 262.24. All right, that's Kelvin. And our temperature did go down by like 30 Kelvin, right? So that's one part of that. That's our first part. The second part says we need to go to degrees Celsius, and we do that by saying K is equal to degrees C plus 273.15, right? And so we're going to plug in 262 right here. And to get that by itself, we're going to subtract 273.15 on each side. So basically just subtract 273.15 from this, and that'll give us our degrees C. And we get negative 10.91 degrees C. Does that make sense? Did it go down? Yeah, it went down about 30 degrees C, which is about correct since that's what we got. Okay, guys, see you next time.